So in this snap circuit video, we're going to look at the computer interface project, which is the CI-73 set. And this is an extension of the SC750 set because it comes with it. You're not going to have this with the SC500 sets and below because those are missing some parts that are used in the CI-73. Now, I don't know if you can get the CI-73 separately or not if you want to experiment with it, but it would basically just be the book here, the interface cable, and possibly the CD if they're still doing that. But I think they're just having you download the WinScope software, which we're going to look at here off the internet, and I will have a link for that so you can download it as well. But if you have a little bit of ingenuity, you can actually make this computer interface cable yourself if you don't want to get it. It's simply just a 3.5mm mono plug with some wire. You could use something like 22 gauge or smaller wire and 2 alligator clips, and that's all that makes up this cable. And then with the software, and you can find the book online, you can essentially get the CI-73 yourself for very little. All you really need is just the interface cable here. But anyway, the other thing I want to mention is that if you have access to a traditional oscilloscope, whether at home or if this is in a school or somewhere and you're actually in a class where you can use actual oscilloscopes instead of the WinScope software on a computer, I would go ahead and try to use that, because a traditional made-for oscilloscope will give you more accurate results, because that's what it was built to do, is take measurements. It was built to be an oscilloscope. So if you have access to that, I'd say go ahead and try using your traditional oscilloscope if you got access to that, and you won't really have to worry about this video because this is an introduction to it, and we're going to talk about the setup of the interface and getting it working with the WinScope software and the computer and everything else to keep in mind about. But I just thought I'd throw that out there if you have access to a traditional oscilloscope, to go ahead and try that with the book here. So with this introduction to the CI-73, we got 3 topics that I'm going to talk about here that kind of help people get started with the CI-73, because I haven't seen anything on YouTube or anywhere else of anyone actually showing stuff really from the CI-73 here. There was only one YouTube video I've seen of the first project, and it doesn't really show or cover a whole lot on it at all. So the 3 topics is that one, we're going to talk about the computer, because I have advice for what you should do on the computer side of it. The second part is the interface, which is the cable and any software settings on your computer, so that the interface can kind of be relatively accurate to what the book is asking for. And then 3 will be the WinScope software itself, kind of a little tutorial on its setup and how the various functions in it work. So the first case is I've got a computer here, and this is an old Toshiba 2400 series satellite laptop, and it's a little worse for wear. The keyboard has some of the keys wiped away, the battery is pretty much no good, the floppy drive doesn't work. I found out recently the optical drive does not work on it, and from the monitor you can see with the string holding it up that there is no spring tension in the LCD monitor hinge. But this computer has decent specs for what we're going to be doing. It's running XP Home, it's got a mobile Pentium 4 processor at 1.6 GHz and a gigabyte of RAM, which is more than enough for our purposes with WinScope, because WinScope was actually built all the way back for Windows 95, so it pretty much can cover a whole broad range of computers. And the whole reason I'm talking about computers and, like they say, using an old laptop here is because I would kind of prefer that people using the CI-73 set, to kind of give them a little bit of precaution, is to not use it on a modern laptop or desktop that you have. Go out and find yourself an old desktop, or of course preferably more an older laptop, off of eBay or Craigslist, some kind of old computer. Again, it can be as far back as the Windows 95 days, as long as it's a working system, to give yourself basically just kind of a cheap junker to have for running the WinScope software. Because if something happens to this old computer that you have, well, hey, your nice modern stuff is okay because you weren't using that for your testing. You were only using an old system like this. Because the thing you have to keep in mind is there is no protection between the snap circuits that you're testing and the computer itself with this cable. This is just straight wires from the alligator clip to the 3.5mm mono input on your microphone connection. So if you somehow get excessive voltage or excessive current through this somehow during testing, and it ends up in your computer, well, then you're pretty much likely going to damage the sound card in the system and possibly other components of the computer as well, again depending on how great the voltage or current was that you accidentally hooked up to it. So by having an older system, you kind of mitigate that risk by not damaging your good hardware that you have for your modern stuff. So, and as I say, an oscilloscope, a purpose-built oscilloscope like I was talking about earlier, is set up to handle that kind of stuff because again it was purpose-built. With the WinScope software that ELENCO is using here, you're using your computer's sound card to basically interpret the signal coming from your snap circuits, and then with the WinScope software be able to transform that to visually show it in a waveform. So you're using the computer sound card in a different kind of purpose. So, and as I say, there's no protection for something like that, so that's why I'm bringing that up. So if you can find yourself an old system, because again this was $30 for me several years ago, so if you can find yourself an inexpensive junker to have just for testing that you can use for other stuff as well, then I say go ahead and go for it. So that's what I have to say about that. Plus there's even a disclaimer on the back of the book here which reads, "Oscilloscope is supplied to you as is, and in no case is the author of this program because somebody else wrote the WinScope software. ELENCO just chose to use it with their systems. They're responsible for personal injury, hardware and or data damage, property damage, or profit loss arising from use or inability to use this software. There is no guarantee implied or otherwise to the fitness of this oscilloscope program for any particular purpose. The software is not intended for industrial or commercial use." So that's ELENCO's own disclaimer, as I pretty much was explaining it to you in my own words, that if you damage your equipment somehow using the cable or whatever and you get, again, excessive voltage or current, well, that's your own fault. They're not liable for anything. So that's why I say be on the safe side and just get yourself an old laptop or desktop or something like that from eBay or Craigslist, and then use that as your testing machine to run the WinScope software on and test your circuits with. So that pretty much covers the whole computer topic. So now we're going to talk about the second part, which has to deal with this interface. So as I said, this is a mono audio cable. So it just has the ground and one input there, and it goes to a 3.5mm mono input, which goes to the microphone in on your computer's sound card. So that's where the signals go. You'll have your alligator clips hooked up to various points on your snap circuits that you're testing, and then of course this will go into the microphone input jack on your laptop or desktop sound card. And usually, again, you can identify the port by just having a little microphone next to a little round plug, and that's where this goes. And then for the computer side, there's a couple of options you need to take into account. So get the camera up here. So for instance, I've got Windows XP on this machine. With other operating systems, it'll vary a little bit. We have our recording volume control settings displayed here, and I have the microphone selected so that the laptop here knows to listen to the input that's on the microphone port here for whatever software is using the recording thing. If we have line in or CD audio or something else connected, then the WinScope software will be listening to that and not necessarily the inputs you have on the microphone where your cable is connected. So keep that in mind. The second thing is the volume control for the microphone input. You see here, computers go from 1 to 7 on the volume scale, and I have mine set around 3 here. Again, yours may differ. You may need to raise it up to increase the gain on the input, or you may need to drop it down and decrease the gain. Again, you'll figure that out as you're testing the WinScope software to see how much gain is being shown on the program. And the other thing to keep in mind is, of course, since it's mono, as you see here, I have the left channel set there. And because of this, again, you only have one audio channel because it's mono here. So mine is using the left channel, yours might use the right channel. And you'll notice this in the WinScope software because for some of you, and I'll demonstrate it as well, the waveform, when you look at it, may appear upside down. So instead of all the waves coming up like this, the waves are actually down below zero like that. And so to correct that, you're going to have to reverse the black and red connections on your snap circuit sets, unless there is an option in your computer that you can reverse the input signals on the microphone. Usually there isn't, so in that case, as I say, you just reverse the alligator clips. That will take care of that problem. The other thing to keep in mind with software is to look for any kind of audio enhancements the computer may have for the microphone port. So in the case of the Yamaha audio that's on this laptop, one of the features it has is microphone echo. Now it's currently disabled, but if that was enabled for some reason, of course we would disable that, because having a echo on the microphone would affect our waveform readings. And some of the computers, in their options, you may find something like a microphone boost option, which basically through software increases the gain on the microphone input. Again, that will also affect your microphone readings because it will make your waveforms appear larger than what is actually being sent to the computer. So in that case, if you have any kind of options for enhancements to the microphone, make sure they're all disabled, because again, those are going to affect your readings in the WinScope software. So now we are going to look at the WinScope software itself. Now, one thing I will say right off the bat, and you probably figured it out by now, is that WinScope is a Windows-only piece of software. They don't have a version for Macs, and they don't have a version for Linux. Now, if you're running Linux or Mac, you could potentially use a software emulator and be able to emulate Windows and then run the WinScope software on that. Although I can't really tell you what to do with those because Linux and Mac are not really my greatest things. Plus, again, working with the emulation software and everything to get the audio piped through it into the emulation software where WinScope is can take a little bit of effort. So pretty much, unless you're using Windows, you may be a little bit out of luck on that part. So, and on the computer here, I'm going to be using Cam Studio. I've actually used this software before when I was showing where to get some free replacement parts and all in some of my initial videos where you were seeing the screen being recorded by itself. So we're going to use this, and that's going to record the WinScope window, and we'll be able to look at the waveform from there while the camera is still looking at the actual snap circuit. So I just bring the camera back over here, and we're going to use Cam Studio on there, and we're going to demo it to show how some functions work. And I'm actually going to hook up the cable here so we can sort of get a waveform showing on it. And of course I'm going to mention it too, again, your mileage may vary because the waveforms that I show in the program may not be what you look like, and they may not look exactly like what's in the book either. Because with WinScope here, we're doing more of a comparative analysis of the waveforms from our snap circuits to what's in the book there. We're not really trying to look at and measure values coming off of it. So then we load up WinScope and then get Cam Studio started. So now we should have WinScope displaying on our video there. And right now it's paused, so it's not displaying any active waveform on there. So looking at the interface here, we have our pause and play buttons. The play buttons will start WinScope and it will start displaying waveforms, and then if we want to pause so we can look at something a little more in depth, we can hit the pause button, and that's where it is right now. Some of the buttons next to it are the trace configurations. We're pretty much just going to leave it in the Y1 trace because we're only using one input here. Now the buttons next to that are some of our time division settings. So the first one is 5 milliseconds per division. And of course every one of these vertical lines is considered a division. and then the one next to that is a half a millisecond per division. So when we need to look at something with a faster rate of time versus a slower rate of time, we can then change the time division of the lines there, and then that way when we look at our waveforms, they can either be wide or narrow depending on the division. Next to that is our trigger settings. So we have a positive trigger, a no trigger, which is turned off where it is now, and then a negative trigger. So with that, and we'll come back to it a little bit later what that's for, to be able to configure it, is that will, when you initially put a waveform on there, it'll look like it'll be going back and forth, because the trigger basically stabilizes it so the waveform holds in place there, because it's looking for a trigger point on the waveform there that we can set, and then that way it will hold the waveform there at what we set. Basically the positive and negative just define if it's going to be a positive voltage or a negative voltage that the waveform is going to hold at. And again, if it's set to none, then it's not monitoring that at all. And we have a couple of other functions like FFT, which we'll look at a little bit later, along with some other functions here in the sample projects. And then one thing we're going to use in particular is the check button, and that basically turns off all gain functions, so it uses the native input settings, like what we showed with the volume control and everything. You're probably going to be using that a lot, because unless you do some gain control adjustment with the sliders, which we're about to look at, you'll pretty much be using that button to let the software just handle the gain and leave that out of it. So this part here, of course, is where our waveform would be displayed. We come over here to Y1, and this is our gain control. So this will show how small or tall, short or tall I should say, of how the waveform is going to look on our system here. And then the Y1 slider that's here, the shorter one, that is going to define where our zero line is. So if we bring it down, our zero line will go further down on the scope. If we bring it up, that will raise the zero marker line up on there. So that way, if we're trying to readjust its position while looking at the waveform, we can do it that way. This one button here is called reset. I'll hit that. You see the slider goes back. We have some numerical values for all our gain, trigger levels, and delay and sweep functions. So T, of course, is our sweep, and this controls our milliseconds per division. So if I change that, you can see our sweep is changing there. And by that we can control the division between the vertical lines here. So that way if we want to stretch out or slim down our waveform, we can do that. We're not going to worry about the delay ones here, and then this is the trig setting, which corresponds back with our buttons up here. So by adjusting where this is, and we'll have a little red line we'll see on there, that will be able to specify where the trigger point is, and then that's where it will hold the waveform at when it has detected the waveform across that point. So let's go ahead and look at some other options before we get started. And again, this is going to be with some settings as well. You can see that I have mine set up to sample at 44.1 kilohertz. Now this gives me the most accurate representation of the waveforms I've seen in the book, even though they're still not quite identical. But you may need to play around with these to see which one gets close. And as far as the sample refresh rate, I wouldn't really worry about changing that setting. Basically 330 milliseconds. Basically, it's taking a sample from the microphone port every third of a second. So that's basically when the scope here refreshes what it's seeing every third of a second. So then we start the scope. Okay, make sure that's reset. We'll start the scope here. So right now, it's just picking up some background noise. And you can see me on the camera here that I'm picking up a cable and I'm putting my finger on it. And by doing that, I can amplify the electrical noise on the computer here, because that's coming in through the charger that's keeping the laptop going. So it's actually kind of intensifying the electrical noise in the computer caused by the charger. And if I click the check button, you see the signal gets a lot smaller because now we have taken the gain control out of it that's on the sliders here. If I take that off, it goes back. And you see that the waveform is jumping around because we don't have a trigger setting. So let me tell it to have a positive trigger and bring this down. It will still jump around a little bit because again, it's not a steady signal. But that helps rectify it some. And then, as I say with Y1 here, I can change the gain. You see the signal looks larger as I've increased it. I'll bring that down, and now you see the signal is getting smaller. As I say, with this Y1 setting, we can move the 0 line around, which raises or lowers the overall point there. And if I click reset, it resets all the values back to where they were. So that's pretty much a short run of how WinScope works there. So now we're going to look at the first 3 projects, which are the tutorial projects. So I'm going to get that all set up here and we'll get to that. So here we are with the first project, project PC1. So you see it's got a slightly different nomenclature than what we've done with the previous projects, which this one is denoting that it uses the computer interface because it says it's the first of the PC project, so project PC1. I'll still have the regular nomenclature, which you can probably see right now in parentheses following from where we left off on the last project. So project PC1 is pitch PC, and say it with me. There it is in the book, and here it is on the board. So we have our traditional oscillator circuit, which again, a lot of the projects in the CI-73 are basically just going to be rehashes of previous projects that we've done. The only difference is that now we've got the computer interface hooked up so we can actually see the waveform coming out of the snap circuit project itself. So I'm going to get the Camp Studio set up, and now I've got the oscilloscope running. So let me go ahead and start it up. So right now we just got some background noise. We don't have the interference from before because we now have it grounded within the snap circuit set here. If I turn on the slide switch, you can probably hear the high-pitched sound coming out of our whistle chip, and if you look on the oscilloscope here, you can see the waveform, but you notice all the peaks are going down below 0, when if we look in the book here, they should actually be going positive. And this is the point I was making earlier. Our connections, although they are correct in the book there where red is, I've just changed in a different position, is actually reversed. So we need to swap around our red and black alligator clips. And now that we've done that, our oscilloscope now shows more like what the book has here. But as you see, they're going off the scale. They're too high. So what we need to do is use our 1-to-1 button, which is the check button that I showed earlier. And as you see, when I click that, it changes the scale down. So now the waveform is more readable to us on the scale there. It's still a little bit on the high side. So now what we're going to do is we're going to change the time scale. Because right now it's 5 milliseconds per division. We want to shorten that interval to half a millisecond per division. So we go over to our button here, and we see now we can see more of the individual peaks, which is what we're trying to look for in the book here. But as you see again, it's not going to be like what the book has. Again, it's more comparative. So we have that, but you notice that the waveform is bouncing around a little bit there, and that's because we have not set the trigger setting. Because right now, without a trigger, the waveform is just going to wander back and forth on there as it's being read every time it refreshes. So this is where our trigger comes in. So you see I have our trigger buttons here, it's turned off. I'm going to set it to positive, and now you see our waveform is not bouncing back and forth there. We can see where the trigger line is. It's right there, and where it's saying if I move our trigger here, you can see that little red line to the left go up and down. And where that is, again, is where it will trigger the recording of the waveform, and that way it's not bouncing around all over the place. So where it's triggered at, we can see the first wave there, and then the delay, then our second wave, and the delay, and another wave, and the delay, and occasionally we can see another one pop up there, which is kind of, as we know, going back to the start here. So that's our waveform there at half a millisecond per division. Well, half 0.5 milliseconds, half a second, whatever. Half millisecond per division, get it right. And that's of course also where we have our slide switch set all the way down. So let me play with this around a little bit here. If we go back to 5 milliseconds per division, you can kind of see all our lines there. Now I'm going to increase the oscillation, or I should say increase the frequency. And if you look at the scope, we now have a lot more peaks displaying on there. And if we go back to our half a millisecond per division, you can see we've got one more spike here showing on our scope. And it's occasionally, again, flickering a little bit to try to show the next one there, which again is wrapping around to the beginning. So we have approximately 1, 2, 3, 4 peaks here, whereas opposed with the other end we had basically 1, 2, 3. So that allows us to visually see the change in the frequency between the circuit there, depending where our variable resistor is. So there's a couple of other functions here, and this is where we're going to get into the FFT. So that, let's see. So FFT is basically our frequency, voltage versus frequency. So if we change this and then go to FFT, you see we get kind of a line graph there. Again, not as perfect as what's being represented in the book here, but you kind of get the idea. And it's not affected by the gain control. We can turn that on and off and it won't affect that. We actually have to use our sliders if we want to change that any. So in this case I need to drag Y1 down, and as you see we're decreasing the gain there and bringing that down. And you see as I change frequency on the circuit, you see our FFT display on the oscilloscope there changes as well. And as you'd expect, the values would be higher with a higher frequency versus a lower frequency. So that's essentially how our FFT setting works. Now we're going to modify the circuit a little bit here by adding in our C2 capacitor, our 0.1 microfarad capacitor on top of that one. So I'm going to change this out of FFT. So we got our waveform going to that. And now I'm going to put this on in parallel. And now notice our waveform has changed on there, and now there's a lot less peaks on there than previously before because we have changed the frequency of the circuit. We've lowered it considerably, and that's being again reflected on the oscilloscope there by when we factor in 5 milliseconds per division, that the frequency of the circuit is a lot less because we have a lot less peaks for every one of those divisions being displayed. And if we go to a half millisecond division, you see with our trigger, we've got it where we can only have one peak showing here, which is right at the start where the trigger is. Try increasing the frequency, and you see we're just getting the second peak there. So again, it's a big difference from the 3 and 4 peaks that we had at half a millisecond per division earlier when we had just a C1 capacitor on there, because we were oscillating at a much higher rate, so a much higher frequency. And of course this allows us to toy around with our gain control, so let me turn this off. And let's bring our gain down some here quite a ways, and then let's play with our time scale and widen those out some. And we can get it about to where it is. But you see, again, we're not going to have a perfect representation of what's in the book. As you see, what the book is looking for is something like this. And you see our representation there, we can't quite get it that way. And again, part of the reason for this, and you're going to find this out yourself, depending on your sound card and stuff, is that any kind of filtering that's on the sound card, the hardware side of it, is going to also affect how your waveforms display. And the book kind of addresses this as well. So it's just something to keep in mind. So that's project PC1. So now let's look at project PC2. Turn that off, and we will stop this. So here we are with project PC2, the Screaming Fan PC. There it is in the book, and here it is on the board. So we got another type of oscillating circuit, but this time we're using our motor as part of it. And I've taken the speaker out and put a 6-volt lamp there because the speaker is particularly loud, and we can actually hear it pretty well through the motor alone. So I just don't want the speaker to make it too noisy. So let me go ahead and get our oscilloscope started. Going and turn our circuit on. I've got the variable resistor all the way to the bottom. There's a little bit of a delay, and then we hit a high frequency pitch coming out of our motor there. If we look from our oscilloscope, it's definitely high pitched because we are pretty much filling the entire scope up. So let me change it to 0.5 millisecond per division and put it to 1:1 scale. And so that's where our settings are right now. I've already got a positive trigger set, so our waveform is not scrolling by there. And let's start manipulating the variable resistor here. And we can see our motor starts to run. And we can see how the waveform is changing as we manipulate the variable resistor, but also the waveform changes depending on our motor. So the motor in that case needs to be running. But you see, the motor, of course, as we know from previous projects, when it's spinning is creating back EMF. So less current is actually getting through here, and we can see that reflected on our oscilloscope when the waveform actually gets smaller. But when the motor is stopped, our waveform gets larger, and that's because with no back EMF being produced, all the current can flow right through there through the oscillator circuit. Yeah, that's just mostly the motor going through there now. And so, of course, you see in our book there, you can see the various waveforms that we're trying to get. Of course, as I say, it's not perfectly going to be like that. But that's what we're getting here, because again, as I say, your mileage may vary. What I'm showing may not be what you're going to get, and what you're going to get may not be what's in the book. So that's why I say we're just kind of checking out the various waveforms. But here we're going to use storage mode, which is a feature here. If I turn on storage mode, you see I'm getting multiple scans overlaid on top of each other. And you see that's what's happening in the book right here. When I look at this waveform, is we get all our scans overlaid on top of each other. Manipulate it here a little bit more. Now our waveform is still bouncing around a little bit, because even with our trigger, so we're not going to get quite a perfect representation with our storage mode, but you can see the majority of the storage is this form here that's getting nice and bold. That's essentially how that works. Now, of course, if we were to use this without a trigger mechanism where it was going all over the place, then you see our storage mode would just show pretty much a mess there, which again is what they're trying to illustrate there in the book. And we can look back at our FFT mode, which is our frequency versus time, or voltage versus time. Make sure here. And voltage versus frequency. You can see the various manipulation going on there. Change our viewing mode. So that's with our just all the way down. And you can see how our FFT scale there changes with manipulation of the variable resistor. We get more peaks toward this end of the spectrum versus where we were further out. And bring it back down. And you can see we're going more and more to the right there. But if we go back up, then we start pushing it more and more to the left there. But that might have to do with the fact that the motor's spinning, creating that back EMF as was shown earlier. And with our high frequency, we get those peaks. But you can see how the back EMF is affecting how it looks here, because it's creating sort of almost a storage mode in and of itself there. If we turn storage mode on there, we see it's highlighting those peaks. Let's stop the motor. That's storage mode with the motor stopped. So let's stop this. So that's pretty much how Project PC2 is, and the waveforms that we get from the screaming fan there. So now we're going to move on to Project PC3. So here we are with Project PC3, the hissing foghorn PC. There it is in the book, and here it is on board. So as before, we've substituted the 6-volt lamp for the speaker there so that it's not as loud, because we'll get pretty much all the audio right there out of our whistle chip. So let me get the oscilloscope going here. And get that started. And when we switch on our circuit, you see it looks pretty similar to Project PC1 when it starts up there. So let me go ahead and switch to our 0.5 millisecond per division, and let's also get the gain off. So again, like PC1, it looks pretty similar, but this setup is a little different, as we'll see when we adjust our variable resistor. See how much different that waveform looks now, and we're getting a little bit of glow on our 6-volt lamp there. So when we look at our waveform, we have a rise and then it's constant, then it drops straight down. Then we get a bit of an exponential curve, where it's like charging something up, and then it goes straight up to on for a little while, and then back down to off, and then it cycles. And we can see that in our waveform there. And of course that rate changes with our setting of the variable resistor there until it's at its highest point. And there are points here, of course, where the circuit doesn't oscillate at all. Of course, see, that's way too low now. I can see I can add a little bit by pushing that. Bring the white just a little bit. So one function the oscilloscope does have here is the wait command. So there's a little button here. I'm going to push that, and then the oscilloscope is going to hold until I get a thing. So I'm going to change the trigger level to 15, and then I'm going to turn the circuit back on. And you see it came on there, and I turn it back off. So now what the oscilloscope has basically done is taken a snapshot at the first bit of data detected at the trigger point there, and now we have that waveform from the initial state of the thing. So we've got the wait command again. Let me go ahead and tell it to reset the wait. Change it here. And you see now, at a different position, we now have kind of a freeze frame of that initial point of the circuit being turned on. So wait allows you in the oscilloscope here to basically take a measurement instantaneously whenever it first detects a kind of output from our snap circuits here on the oscilloscope. So that's how the wait command is, and that's basically what they're demonstrating here in project PC3. Let's see, is there anything else? Yeah, just having us look at the frequency spectrum again, we can do that. Where we go to the frequency spectrum here. Again, our gain is a little on the high side, so I will show adjusting it here. That way you can see how the frequency spectrum changes. As they get bunched up toward the left end there. And then start going to the right. Once we get to about there. Stop the oscilloscope. And so that's pretty much what there is for project PC3, and pretty much concludes this introductory video to the CI-73 system.